So now we're looking to continue with the test in a little quieter environment. So I got a C8. You want to know which one of these is non-polar. That means it's not polar. So if you draw the dot diagrams, now I'm just going to throw these out here. You're going to have to follow the rules, you know, add the valence electrons and so on. But that's your dot diagram for CH2O. BRF3 would look something like this. And then what you're going to have is 7 times 3 is 21, and 7 more is 28 valence electrons. So with 28 valence electrons, you'll end up with 2 extra, and they need to go around the center. So we end up with 5 domains.
Please excuse this interruption. With Noah Trevino, please report to the front of the school. Noah Trevino, please report to the front of the school. Your Uber is waiting. Thank
So you have 5 domains, and the vectors are not going to cancel. See, they're going to move. They're going to move in this direction, and in this direction, and in this direction. So that it'll be a polar molecule. Whoops, hit the wrong button. Okay, this molecule looks like this: HCN. And that's going to be linear. The electrons are going to move this way. Whoops. They're going to move this way and also that way, so they won't cancel. CO2, linear molecule. They go this way, they go this way, so the vectors can't, oops, that's supposed to be straight out. So the vectors cancel, and it is a non-polar. So the answer is D on that one. 90-degree bond angles. Once again, you got to draw the picture. So water looks like this. Ammonia looks like this. CCl4 looks like this. That'll be a tetrahedron. You have 6 electrons and 6 electrons and 6 electrons and 6 electrons. SO3 will look like this. So that's going to be trigonal pyramidal, or excuse me, trigonal planar, because there are 24 valence electrons, so you needed 2 more than you had, so you had to share a couple. By the way, would this exhibit resonance? Yes, and because the double bond could go in more than one location. And if you look this molecule up on the internet, you most likely will find it looking like this. And the reason they do that is to expand the octet, which minimizes the formal charge. So if you look at sulfur that has 6 valence electrons in this picture, and then -1, half of all, there are 12 shared electrons, so half of that's 6. So 6 minus 6 equals 0. Down here, the sulfur would equal +2, because you have 6 minus 1, 2, 3, 4, which is half the shared minus no unshared. So I did that in a different order than what I taught you, but so it's 6 minus 0 minus 4. Either way, it equals 0. All right, so the formal, oh, excuse me, either way, it equals 2. Sorry, I started moving in my head to the next question. So this is not as good a picture as this, and that's why you see this expanded octet. Then the XEF4, it'll look like this. It'll have fluorines in a square, like that. And then it has a pair of electrons up here and a pair of electrons down here. So that's a square planar. And these bond angles are all 90 degrees. So it doesn't look like 90 degrees the way I drew it, unless you start thinking about it three-dimensionally, then you can see it. Okay, number 13, which one requires the expansion of the octet in order to minimize the formal charge on the central atom? Draw the dot diagram. So you got HOH, looks like that. PH3 looks like this. CCl4 looks like this. And SO4 looks like this. All right, so, and let's see, the SO4 would have 26 times 4 is 24, so it's 32 valence electrons. So if you put 6 in here, and 6 in here, and 6 in here, and 6 in here, it all works out. However, the formal charge on the sulfur is 2. Here, the formal charge on the carbon is 0. Oxygen, it's 0, not oxygen, phosphorus, it's 0. And oxygen is 0. But the sulfur's 2. So if I were to draw this picture with a double bond in 2 different places, I'm just going to draw this in 2 dimensions because I'm out of space. So if you do that, now this formal charge on the sulfur is 0 because it's 6 minus half of 12. So it's 6 minus 6, which gives you 0 for a formal charge. So you had to expand the octet, which means there'd be more than 8 electrons around the sulfur. Okay, in this case, ionic bonds, ionic means metal and nonmetal, or metal and polyatomic ion. So you want neither compound to have an ionic bond. So this is a metal and a nonmetal, so that's ionic. Metal, nonmetal, that's ionic. Metal, polyatomic ion, metal, nonmetal, that's ionic. Metal, polyatomic ion, that's ionic. So all 4 of those have at least one ionic compound. Any compound between 2 nonmetals will always be covalent, sharing electrons. So the CH4 is covalent. I'll put a C there. So covalent there and covalent there, but we want both elements to be covalent, or both compounds to be covalent, so the answer is this one, because that's nonmetal, nonmetal, and nonmetal, nonmetal. Which one's pyramidal? So you got to draw the dot diagrams. So NO3, when you draw it, will look like this. I just use that for 6 electrons. Sulfur trioxide, we did that a minute ago. It'll look like this. Of course, if you look it up on the internet, it'll show an expanded octet. ClO3 minus will be, this is your answer because ClO3 looks like this. You have 7 and 6 times 3 plus 1. So 6 times 3 is 18 and 1 is 19 and 7 is 26. So valence electrons, so you'd have a Cl in the middle. Then you have an O coming off here, you have an O coming off here. I don't like the way I'm drawing this, but try it again. Cl here, put the O on the bottom, O here, O here. Now we've got, of our 26, we've got 6 in the picture, so you got 20 to put in. So when you put in 20, you'll have 6 here, 6 here, 6 here, and that's 18, 19, 20. So this unshared pair on the top makes it a pyramid. Okay, which one has 3 pi bonds? I don't know. So we have to draw these. So you have a CHOCN. So we know that you're going to have an H and a C and an O and a C and an N. I don't like that picture very well. Let's go to this next one is HCCH. I'll come back to that in a minute. So HCCH and then CN. You know that this is not going to be your answer because the dot diagram on that one's going to look like this. But anytime you have 2 atoms, you can't have 3 pi bonds because you can only have the maximum of 3 bonds between 2 atoms. So 3 pi bonds would require 4 bonds because you always have to have a sigma bond. Okay, CO2 looks like this. We drew that earlier, so that's not the one. CO3 has resonance. So that's not the one. All right, so the answer has to be this first one. Oh, well, no, we didn't do the second one. So this has 4, 8, 9, 10. Take away 6. You'd have 4 to put in. So 1, 2, 3, 4. So you're 4 electrons short. But those electrons are going to have to go. You're 4 short, so you can't put it. You're going to need a triple bond or 2 double bonds, but you can't use 2 double bonds because hydrogen can't handle the double bond. So it's going to end up with a triple bond between the carbons, and it'll look like this. Now you've got 10 electrons, 2, 4, 6, 8, 10. All right, so now let's go back to this one. And this is going to have to be our answer. So we're going to put, I think we're going to have to do this, I believe. O, H, C, N. Let's try that. So there we go with 4, 8, 13, 14, 20 valence electrons. So if we have 20, we have 2, 4, 6, 8, 10. We have 10 left to put in if I drew this picture. How many did I say? 10? So 20 minus 2, 4, 6, 8, 10. So I have 10 left to go. So if I put 6 here, and then 1, 2, 3, 4 there, that's an acceptable picture. But it doesn't show our triple bonds, does it? So I'm going to stop the film for a minute. I'm going to think about that one just a second. I'll come right back. So I'll be right back on, this will be video 3. This one's getting kind of long anyway. So we'll start video 3 coming up with that question.